Hello, this is Math 2270 coming to you from the College of DuPage during the summer of 2020. And this is the lecture reduction of order. In the preceding section, we saw that the general solution of a homogeneous linear second-order differential equation, shown here with variable coefficients, is a linear combination y equals c1 y1 plus c2 y2, where y1 and y2 are solutions that constitute a linearly independent set on some interval I. Soon in this course we will examine a method for determining these solutions when the coefficients of the differential equation shown up here are constants. This method is a relatively straightforward exercise in algebra, but does break down in a few cases and yields only a single solution, y1, of the differential equation. We need two. But it turns out, fortunately, that we can construct a second solution, y2, of a homogeneous equation 1 even when the coefficients are variable, provided that we know a non-trivial solution, y1, that means not identically equal to 0, of the differential equation. The basic idea described in this lecture is that this equation can be reduced to a linear first-order differential equation by means of a substitution involving the known solution y1. A second solution y2 of this equation, again, is apparent after this first-order differential equation is solved. Let's look at an example, and this example is intended to illuminate the path we're going to go on. So let's start with a simple differential equation, y double prime minus y is equal to 0 on the interval from minus infinity to infinity. Now, note that y1 of x equal e to the x is a solution, because every time you take the derivative of e to the x, you get e to the x, so two derivatives would give you e to the x minus e to the x is equal to 0. So that is a solution. But now what we're going to do is we are to assume the general solution is given by y equals some unknown function u of x times the known function y1 of x, and so in this case this would be u of x times e to the x. Now what we're going to do is substitute this general solution into the equation that we have. So we're going to have to take the first derivative and the second derivative, and we will have to carefully use the product rule. Now note, when we take the difference of these, which is up here, what's going to drop out is this term, because it's going to be positive here and it'll be negative over here. So you see we have now a differential equation that's going to look like this when we simplify it. And notice that there is no term involving u anymore. And since e to the x times this is equal to 0, e to the x is never equal to 0, that means this must be equal to 0. So you see we have a differential equation that doesn't have a u in it anymore. That means it is useful for us to make the substitution w equals u prime. And if I do that, then I get this, w prime plus 2w is equal to 0. Now this is very nice because this is a linear first-order differential equation. We know how to solve that. I'm going to skip the details, but you should put the details in as practice. So we find out that this expression really is the same thing as having the integrating factor ends up e to the 2x, and so we end up with this is equal to 0 once we multiply all the way through by e to the 2x. And then we can solve this by integrating both sides, and what we will get is that w is equal to c1 e to the minus 2x, and that means that u prime, which is what w is c1 e to the minus 2x. But that means I could integrate this again to find out what u is. So I integrate it again and get this as minus 1/2 c1 e to the minus 2x plus c2. But then, remember what we were doing is u was up here, so I take that times my y1, which was e to the x, and I get this expression. Now, these constants could be anything I want. If I pick the constants this way, C2 to be 0 and C1 conveniently to be -2, we see that, oh, y2 equal e to the minus x is also a solution. And because this Wronskian taken with e to the x is not equal to 0 for every x, the solutions are linearly independent on -infinity to infinity. So since we have shown that this and this are linearly independent solutions of a linear second order differential equation, the expression is in fact the general solution for this. And when I say the expression, I'm talking about this expression over here on -infinity to +infinity. Now, our path is a little bit more complicated, but this is the process I recommend. We will conclude with an equation, but I recommend you follow the process. Don't try to memorize the equation and then do the integral. Anyway, here we go. So we start with something that has variable coefficients, a homogeneous linear second order differential equation, and we do what we always do. We divide all the way through by a2 to put it into this form. We're going to assume we know a y1 that is a known solution to this equation, and that it does not equal 0 for every x in the interval. This is an important detail that we will need later. And so we say the general solution then, y is going to be u of x times y1 of x. So now we're going to take this and we're going to substitute it into this equation. So we take the first derivative and the second derivative, and we plug it into that equation. Actually, we're plugging it into this equation, excuse me. And we do the calculations and reorganize things. And once again, we see that since y1 was a solution to this equation, this factor shown in blue is 0. That means we're dropping out by design the term having the u in it. And so when we simplify this, what we get is this expression, which is a equation without a u, and we can do the substitution w equal u prime to get this. And again, this is going to be a linear first order differential equations, and in fact you can even separate variables on this, I suppose. Now you know how to solve this, and I encourage you to work through the details of the solution. But what we're going to find out when we solve that, this is separating the variables and integrating, what we get is that the ln of absolute value of wy squared is equal to minus the integral of p dx plus c. We exponentiate both sides, and we have that w is equal to w times y1 whole squared is equal to c1 e to the integral of minus px, and then I can divide by y1 squared. That's where I'm using the fact that y1 is not equal to 0, and so I've solved for w. But now we're going to use the fact that w was u prime. So what we're going to do is we're going to integrate yet again. So we integrate this, and we add a constant of integration. Now this is true for any of these constants, so we can choose c1 to be 1 and c2 to be 0, and realize that this is a second solution to the differential equation. And it makes a good review of differentiation to verify that this function is in fact satisfies the equation, and that y1 and y2 are linearly independent on any interval on which y1 is not 0. I would encourage students to do this. So now here's a problem for us to do. You want to find the general solution, and in fact a second linearly independent solution to this differential equation. Notice that we do have variable coefficients here, given that y1 of t equal t to the minus 1 is a solution. You should probably verify that to start with and then go from there. Beyond that, you know what to do. And I will see you in 15.1.